Zinyongo, and I'll be talking about our module code, the bouncer. So first we have our input clock, which is used to increment the count when noisy and clean button are different. And then we initialize our noisy button, which is the button on the FPGA system, which has mechanical bouncing. And then we have our output clean button, which we initialize to 0, and this is what removes the bouncing. So we first initialize count to a 17-bit count of binary values and instantiate a wire max count equal to 131,071 clock cycles, or a 17-bit array of ones, which is 2 to the 17 minus 1. And then we start our loop saying at every positive edge of the clock, if noisy button and clean button are equal, then count does not increment. Else, if they are different, we initialize count and increment by 1. And if count equals max count, then we are to say clean button is equal to noisy button, meaning that they've been different for a long enough time.
Hi, I'm Jonathan. I'll be breaking down the Morse encoder module. This module allows us to input dots and dashes via buttons and stores them in a binary format. Here's how it works. To start, our input consists of a clock alongside our 5 buttons. We have a button for dot, dash, enter, reset, and back. It then outputs our final sequence in, which is a 40-bit output of our stored Morse code sequence. We then have our final number of in, which is a 24-bit count for our dots and dashes, and then a 3-bit character position out, which keeps track of our current character position. Our register stores our temp values and are initialized to 0. And then at each clock cycle, the system will check for which button is being pressed and then updates its previous button state. Then we will be looking at which button is actually being pressed. If the reset button is pressed, this will clear all values, resetting the entire sequence. And then if the dot or dash button is pressed, we will increment the input value and make sure that the input value doesn't exceed 5, since our Morse code character, none of them exceeds 5 inputs. And then from there, we store our dots and dashes as 0s and 1. So in our sequence variable, it will just sees it as 0s or 1. And then when the enter button is pressed, this will save the sequence to its respective memory. And then the final output will take in the values of these temporary sequences. If the undo button is pressed, the back button is pressed. This will then move the character position back 1 and then store and then reset that position value to 0s and then update the final value.
This is our Morse decoder module, which takes a 5-bit binary input called possible chars to handle up to 5 dots or dashes. It also has a 3-bit binary input called possible inputs to account for all 6 possible combinations of dot-dash sequences, such as no dots up to needing all 5. Our output variable called display is a 7-bit binary array which lights up our 7-segment display. This block of code initializes our buffers or blanks. We use buffering for characters that don't need 5 inputs. For example, a blank space uses 5 blanks as it has no dot or dash input. Our decoder initializes the Seiko alphabet for our 7-segment display, which provides a unique representation for each letter and number. This is why the letter S has the missing center line, making it unique to our number 5. Other characters such as X and W are outputted in a new way because the 7-segment display can't depict diagonal lines. As an example of how we get this random series of 1s and 0s, I will go over how we output the letter F. This image shows the indexing of each segment on our 7-segment display. F requires segments 0, 1, 2, and 6 to be on. Segment 6 is our most significant bit, hence why we have the leftmost 1. Segment 0, 1, 2 are our 3 least significant bits, hence why we have 3 rightmost 1s. This always block handles all 6 cases of potential input sequences. For example, if the input is just a dash, we use our 4-space buffer to complete the entire sequence and convert the single dash to the letter T. In our code, we initialize dashes to binary 1 and dots to binary 0.
Green FSM, we have a clock input, a final sequence of inputs for our final 8-character array of input sequences. Final num of in then describes all possible 6-number input entries per character. Then we have a 7-bit display variable for our 7-segment display output, 8 character positions, and the clock divider to stabilize the display output. We then have a max count, which is 17 bits because we found that a max count value of 100,000 provides the best clock divider value for our VGA and FPGA display output. We then have our decoder inputs, which are then instantiated down here, where based on those 5 input sequences and the number of inputs that you enter, you receive a certain display on the FPGA and VGA. Now we have a display state, which is also based off of the 8 possible cycling display positions of the FPGA on the 7-segment display, and we use 1-hot encoding of that display position, which is read from right to left in terms of our 7th display state representing the first character position. So when the display state is having a value of 7, we end up using the first 5 input sequences and the first 3 number of inputs to determine what character should be displayed within our first display position. This is our last letter module, which is somewhat similar to our screen FSM. We have a clock divider, which makes the clock 4 times slower, character position, which is 3 bits to display up to 8 display states, and then we again utilize final sequence of in, final number of in, and our 7-segment display output. These again are decoder inputs. We then instantiate it one more time. However, we now have 8 possible static display states instead of the cycling that would be done if we were to use the FPGA's 7-segment display. Knowing that these positions are static, we'd use 7 minus our current position to set the position of the first character to be our display state. And again, since the decoder's reading these character positions from right to left, our 7th display state would utilize our first 5 bits of a final sequence of in and our first 3 bits of our final number of in to determine what character should be displayed in the first display state.
Now, I'll be breaking down the VGA controller module. This module is responsible for generating the VGA sync signals and display of the 8 characters by calculating the pixel address and turning the pixels on and off. To start, our inputs consist of the clock, display position, and then our fixed address. And then for our outputs, we have our horizontal sync, vertical sync, and LED on. Well, in this case, LED on is just our pixels. For our parameters, these were specifically chosen to define the VGA resolution and sync timing. We have our wire enable, which ensures that only the pixels within the active area, the 640 by 480, are displayed. Our registers, each of these are responsible for each character being displayed. And then for our case statement, our display position, this allows only one character to be displayed, and it determines which of the 8 to be shown. To determine this, it will go through the current pixels with position and height position and ensures that it's within the boundary and then activates the correct or corresponding letter. My actual address takes the value of address letter 1 and ensures it is displayed in the correct position, and LED on ensures the same thing, but in this case, if the pixel should be on. And then we call on ASCII ROM to retrieve the correct pixel values based on the given input. And then for each of the displayed letter, this will calculate the correct memory address accounting for the vertical offset. This section of the code basically increments so it can go through every single pixel on the screen. And for our horizontal and vertical sync, these will only be active during the active video area. And finally, based on the display letter, these will only turn on the correct pixels in its respective width position, which can be seen from the width shift.
We are Team 2, dot dash, and I'll be presenting our Morse code translator. We will start with one-letter inputs, such as 1 dash, which is a T, and 1 dot, which is a E. A dot and a dash gives you an A, and if you enter without any inputs, you get a blank. 3 dots will give you an S. With 4 inputs, such as dash, dot, dash, dash, you get a Y. This is our delete button on the bottom. When I click it twice, we get rid of our S and Y. 5 inputs gives us numbers, such as dot, dash, 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 dash for 1, and dash, 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 dot for 9. This is our clear button on the top, which will clear the entire display.